last class, we mentioned about gradient. Okay. So basically, the gradient operation operates on a scalar function. Right, so you have a scalar function. It is a perimeter of space, two-dimensional, three-dimensional, but it is scalar, meaning there's no direction, there's only value. You perform its gradient, you're trying to find the maximum amount of change in certain direction. So we use the map of height to serve as an example. So after you perform the gradient operation, you have a vector. So today, we are going to introduce another operation, which is called divergence. Okay. So mathematically, divergence is written as the same inverted triangle, but now having a dot function. To remind you, this operation is working on a vector. So I'm using the color yellow to denote a vector, and the green one to denote a scalar function. So divergence and gradient are somehow reversed. Divergence works on a vector function, but then you arrive at a scalar function. Right? So this is in contradiction to gradient. Gradient operates on a scalar function, and you result in a vector function. Okay, reversed. So we can turn off the light. So now let's come back to the part plane. Before we begin, let me show you a nice picture. Divergence for fun. Right? So math can be fun. So let me show you a very beautiful picture. So this is something you go into a water park, and you might see this. So magically, there is a water outlet, right? There's no water coming in because there's no wall. But magically, you have water flowing out. So think about it. Try to relate this magical water outlet to divergence, and then try to understand what does it mean when you perform a divergence on a vectorial function. So there's no water coming in, but there is indeed water coming out. So if I ask you to calculate something, right? For example, I have a box. I have a three-dimensional box to surround this entire outlet, and I ask you, what is the net flow of water coming out from this yellow box? From this side, no water coming in. This side, no water coming in, no water coming, only water coming out, right? No water coming in, no water coming in, here, and the back side. So there are 5 sides without water coming in or out, but there's only one side having water coming out. So you will answer me, this is really magical because somehow we just have water coming out, right? But this really contradicts to our understanding. Usually you have the wall, the outlet. You know water is coming in from this side and water is coming out. So there's no net flow of water. But in this case, if this is true, of course you know how it works. There's a center tube having water coming in, then it's just coming out from the outer tube. So the total mass, the amount of water, is still conserved. But I'm using this example. If you don't know the trick, how it did it, in the space, you just have water coming out. And that really relates to what divergence means physically. The meaning of divergence is you're trying to sample the net outward flow or flux of your vectorial field in a small value, a three-dimensional value. Okay? So this is what you have to remember forever. As you can see, the way I'm teaching vector analysis or calculus, I'm not emphasizing on the derivations, but rather on the physical meanings. If you can understand and embrace the physical meanings, you don't really have to memorize a lot of things. Right? So for divergence, the definition is you're trying to sample. So you have a vectorial field. A vectorial field A may be drawn as these lines. Okay, so it's like some kind of flow of water. So for me, the best analogy to think of the fields is like water, because we encounter water every day. Water is like something flowing with certain velocity and direction. So it's a very nice analogy, example, to serve for our understandings. So you have some flow of fields or flow of water, and you just place a cube, right, into it. And you ask yourselves, what is the net flow of water in that cube? So in this case, water is coming in from the left-hand side, this surface, and the same amount of water is flowing out on the right surface. So the net flow of that vectorial field is 0. Now, if you have the definition and you come back to this example again, you have your space, right? You use this yellow box, the three-dimensional box, to surround this outlet. And then you ask yourselves, what is the net outward flow of field? Field here is represented by water. Ideally, if you don't know the trick, you have water flowing out. So the net outward flow is positive because water flowing out is outward. Okay? So it is positive. So if you have a divergence of a vectorial field, meaning the net outward flow or flux is positive, then this is telling you in the space you surrounded, there is a source of the field. Okay, so this is a flow source. So let's come back to this picture. So somewhere you know this yellow box is giving you water. So if you ever become thirsty, you just go there, right? It's magic. You just go there, you don't have to provide water, but you have water you can drink. Of course, it's magical, it's just a trick. But on the other hand, if the divergence of that vectorial field is negative, what does that mean? You perform the divergence on a vectorial field, but then you have a negative value. Scalar can be positive or negative. It doesn't matter. But if you have a negative value, it means water or field is flowing into it. Right? So basically, I didn't mention about the flowing direction, but ideally we think due to gravity, water is flowing downwards, right? So this is flowing out. But it can also flow into the outlet, right? So in that case, if you have a negative divergence, water is flowing from the bottom to the up. This is more magical. So I pretty much gave you the definition. Again, try to repeat after me. Divergence works on a vectorial field, and when you perform the divergence, you're trying to calculate or trying to ask what is the net outward going out. If you have a positive value, you have fields going out. Okay? The net outward flux per unit volume. So this is something you have to remember. The meaning is you have a three-dimensional solid structure and you are trying to sample how much of the field is flowing out. And net means you might have certain surface flowing in, so it takes on a negative value, but then maybe another surface is flowing out, it takes on a positive value. So positive and plus negative, does it go to 0? So this is extremely important for you to understand. Right? So mathematically, I know you hate math, so do I, but let's try to write this sentence using a mathematical equation. For me, if you can write something to represent some wording, you feel you are superior, you're better, you're good. Okay? So divergence, defined as the del operation having a dot on a vectorial field, is defined as for a very small value, right? Unit value. So in a very small three-dimensional structure, it has its own value. It has a lot of surfaces. So within this very small value, I'm trying to calculate the net outward flow of that field on all surfaces. The all surfaces is included by this integration sign, and with a closed circle, meaning I have to calculate all the flows on the surfaces. So in this example, I have a small cube, right? So the cube has its value, but for a cubic, how much surfaces do I have? 6, right? So according to this definition, if I really want to calculate divergence of A within that volume, I need to calculate all the outward flows or flux on all 6 sides. I calculate the flow for one surface, and then I have to add the flow, outward flow, for the second surface, and so on. So totally for this cubic, I need to perform 6 calculations to accomplish this closed integration on all surfaces. Right? So I'm spending a lot of time to tell you the basics, the meanings behind the mathematical equations. But this is a definition, and this definition follows directly from this sentence. The net outward flux per unit value, right? Per unit value, net outward flux. Right, clear enough? And let's move on. All right, so let's really calculate it. I have a small cubic. A cube has 6 surfaces. So I'm not going to do all the calculations. I'm only going to calculate for 2 surfaces. The rest are for you to work, and I believe you learned this in the past during your first year, freshman year. Okay, so I now have a cube centered at point P. So P has its x, y, and z values. x0, y0, z0. So as you can see, I'm using x, y, z. So which orthogonal coordinate system am I working in? X, y, z means I'm working in Cartesian. Why? Because I'm too old. You're young and smart, so I usually work in the easiest coordinate. I'm only trying to tell you, to give you a guidance to how to formulate divergence in Cartesian coordinate. The rest two coordinate systems are left for you as your homework. Okay. All right. So I have a vectorial field A. It's also a function of x, y, z. It's not surprising because I'm working in Cartesian coordinate. So I have the x component, y component, and z component. So I have three components. Each component is having its own direction. Okay, so that's a vectorial field. So somehow, for now, from demonstration purpose, I want to calculate the outward flux on this front surface. Okay? So this is the point where you have to think. Why did the professor spend so much time in teaching you differential length, differential surface, and differential value? Let's come back to this definition. ds. What is ds? Differential surface. What is delta v? Differential value. So everything, differential surface, differential value, are actually coordinate dependent. So this is the point where in the past you just try to memorize everything, right? Divergence for spherical coordinate, very complicated. But I'm teaching you how to derive it. If you know its definition, you understand about differential surface, differential length, differential value, you don't have to memorize anything. Okay? So, I want to evaluate the flow, the outward flow or flux on this front surface. The first thing you have to ask yourself is how to properly formulate this ds, the differential surface, for this front surface. You might just wonder, let me draw a picture for you. So you have a surface, right? You have a surface. Ideally, a surface has no thickness. So basically, you might be wondering, oh, the surface can actually have two directions. One is going out, the other one going in, right? So for a given surface, you can have two directions. But now the fact is, this surface is a part of a three-dimensional solid. Okay? Solid structure. This surface is the outer end of a given three-dimensional solid structure. So for divergence, we're trying to evaluate the net outward. So I'm emphasizing the wording outward, going out. So in this case, this surface has a well-defined surface direction going out. You don't want to evaluate the flow with a wrong sign for the surface. I mentioned repeatedly, surface is itself a vector. Okay? So for divergence, we're trying to evaluate the flow going out of the box. So for this surface, we want to use this direction. And for this surface, I want to use the outward. And for this one, going out everywhere, right? Everywhere going out, going out. So let's come back to the PowerPoint. So how to properly formulate this differential surface? The direction for this guy is pointing outwards, so it must be in the positive x direction. So once you know its direction is in the positive x direction, its area must be determined by the other two coordinates, right, in the y and z directions. So its magnitude, its surface area, must be delta y, delta z. Again, this is coming back to what I emphasized. For a given surface, you have the direction, and then the magnitude must be determined by the other two unit vector directions, right? So you have x direction, but then the magnitude is determined by delta y, delta z. So you know how to formulate this ds, right? So now, ds, a vector, is making a dot product to the vector field. But the vector field is having its own x component, y component, and z component. So in this case, for this particular surface, which field component of A is being evaluated? X, y, or z? Your ds is only having the component in the x direction, so only this one is being evaluated, okay, at this surface. Because you know ax dot ay or dot az are both 0. Okay? So for the surface, it only samples how much flow of ax is there. Right? But then you have a question. Because this cube is centered at x0, y0, z0, but you know its dimensions, delta x, delta y, and delta z. So apparently, this front surface has this coordinate value other than x0, y0, and z0. So the surface sits on the x value of x0 plus delta x divided by 2. Right? It's having an offset in the x direction. So I really need to calculate. What I'm trying to calculate is ax component, but having an offset in the x direction, the x coordinate value, but not in the y and z. Okay. So how to do this? How to evaluate this? This is based on the understanding of Taylor's series. When delta x, delta y, delta z, right, is delta x, delta y, delta z are very small, we can confidently use Taylor's extension to the first order. So this field value is probably equal to ax evaluated at my center point plus an offset of delta x divided by 2 and multiplied by the slope, right? The physical meaning of Taylor's expansion is you're using Newton's method, right? So if you have ax itself having a partial differentiation in the x direction, you're trying to find the slope. And then you multiply by the offset, you probably know ax at this location, at the surface location. Okay? So now you have these two terms and you multiply by the surface area. So together you have these two terms. I'm using the color. So now because you have delta x multiplied by delta y and delta z, what is delta x multiplied by delta y multiplied by delta z? For Cartesian coordinate, that is the differential value that we covered. Okay, so that is differential value.